Geomorphology, and we're going to be measuring a variety of different things in a stream. But our takeaway is going to be a profile of the stream bank, which is going to be fantastic for monitoring year after year. But we'll also get an assessment of the volume of the water in the stream and the flow. And so you can compare that seasonally too. And depending on the different flow and the different volume, you're going to have different habitats for different organisms. We're going to be graphing initially. We're going to be taking some data along our line of rope here that I colored with a paint pen so that it doesn't slide when you water it. But these are all stuff pieces you can get at camping stores or hardware stores. It's just 3/8 nylon line, 10 stakes, a little bit of surveying tape, and meter sticks. We want to do everything in metric. So as we go along here, we're going to take measurements. And we determined that for this width of stream, what do you think an accurate or an appropriate distance do we want to measure across the stream? I have marked out on the rope 10 centimeter increments, but that's a lot of data if you're going to have your students come out here and do this. So we chose a larger increment. Any thoughts on how far you want each measurement to be away from each other? Half a meter? Half a meter, that's exactly what we did. It's really up to you. If you have a teeny tiny little rivulet and you've got banks right here, you probably do want to do it every 10 centimeters. But in this case, it's about 5 meters across, so we figured half a meter is about appropriate. Your goal is to at least have 1 or 2 measurements in the water, and when you are measuring along an increment that touches into the water, you will not only identify the distance from the rope to the bank, but you will measure how deep the water is. And your data sheet has a place in there for you to do it. So this data sheet and this resource will walk you all the way through it. So if I'm going to go quickly through the directions, but if you forget everything I've said, you'll be able to take this and it'll walk you through every single step. Your first increment is going to be at the 0 line. You're going to measure the depth from the rope to the ground, and then you can choose what increment you do. We did 50 centimeters each time out. So any questions before we get started? I recommend you work with at least one other person. We have 2 different lines set up. After you do your data, you are going to graph it on the page behind the data sheet.
Are you just doing one line or both?
You can just do one.
Just do one. You're going to have the tendency to want to bend over and look, and your measure stick is going to, either if you're checking it this way, it's going to lean away, it's going to give you a bad measurement, or if it's down in the stream and you have to get your water level reading, you're going to also tend to pull it back so that you can read it, and when you pull it back, again, that'll give you a skewed reading. If in your streams you have shoal or a cobble bed like what I'm standing on right now, you or your students may be tempted, if you get on top of a boulder, or this is a clay plug actually, you're going to be like, well, this isn't really on the bottom, so I'm going to move it a little bit over here, I'm going to move it a little bit over here. But what you want to do is actually just keep it exactly where your measurement says, because the next time a storm comes through and this isn't here, that would be something to note. Or, you know, man, we had a huge flood and there was a lot of water racing through here and it managed to stay exactly where it was the last time. Again, that's another thing to note. So it's going to be tempting to be, you know, on the bed, and if it's cobble or sand or something that gives, you're going to also be tempted to push down to get a true reading, which you don't want to do that either, for the same reasons. Stuff is going to move, which is fine, because as opposed to the other stations, this isn't so much a rating as like good, poor, excellent, fair. Literally, this is to see what is here and to track any changes. So no connotations connected to the changes that happen.
And you can categorize your stream based on how large the volume is and how fast the flow is. It'll tell you something about what to expect. You have to do what's appropriate at your site. You can leave a little surveying tape. One of our stream biologists suggested putting stakes out even further where you know the water is not going to come through, and marking those stakes in the ground, so a little bit higher up across from where you measured, so you can still get a bird's eye view across to identify where you put them. Okay. But if you leave anything right here, the chances are it'll get washed away in the rain. You can also, in some cases, and I'm not going to recommend this, but you can spray paint trees that are in the right place, or use a little surveying tape or mark it with a GPS, although that's not quite as accurate. Take pictures.
Pictures would be good. So if you have a smartphone or if you have an iPad through your school, there are free apps that say, like, pretty much it's like Mark My Spot. And what you do is you tap it and it'll say, you're at, and they'll do it in decimal degrees, 36 point bunch of decimals, and then negative 73 point bunch of decimals. So if you keep that and you walk out with your phone or your car GPS and you find the spot, if you can't physically leave a mark on your stream.
55.5.
Another trick is to not move your meter stick until you count to the next spot.
Gotcha. Thank
So for us, it was 88 centimeters and 86 centimeters. So together, 174 centimeters is what we got for our first width. And then the average water depth, you should have this information already from when you measured doing your profile, when you did, of the 76 centimeters that is the distance to the stream bed, 4 centimeters is covered in water. So you should have that already in your data chart. You just add those numbers together plus one of the zero values that takes into account the bank. And so for us, we had 4 data points that had water corresponding with the data point. So we had 4 data points plus a 0 data point divided by 5.
We add that 0 data point because we want to get a representation of the water sloping back up to the bank. So you add 1 0 point to your data points. This is the standard protocol from the EPA, and I know it's not very intuitive, but you add 1 0 data point on top of it, and then you divide by your data water measurements plus a 0. If you had 3 increments in water, you add a 0, that's 4 increments. So you add the total and divide by 4. Okay? Yes?
So we only had 1 measurement that wound up in water.
So your measurement?
3.3 should have been divided by 2.
Yes.
Right.
Okay, so then that'll be your average depth. So, and that is centimeters. So below, you're then going to calculate the area of the cross section. So now you have your width and you have your depth. And in case you forget how to calculate area, we told you how to, so all you have to do is follow along. And this is where you can also explain to your students how units of measurement change. So you have centimeters multiplied by centimeters is not centimeters, it's centimeters squared because you're getting the area of something. So then what you're going to do is take your centimeter squared value and divide it by 10,000 because that's the conversion unit.
To get to meters squared.
Yes. Okay, so now you have your area of your stream section that you've monitored. So the next part we're going to look at is the flow rate. How quickly is water passing through your cross section? So that part is, I think it's the fun part.
It is the fun part. Actually, well, let's have the students do it. So this is how we measure flow.
I'm in the chart.
So what you're going to do, you're going to have a start point and an end point, but it has to be in a riffle. Okay, well, a riffle is an area of the stream where there's it's low depth and there's rock on the bottom, basically. So it flows much quicker. It's not very deep like a pool, and there's little movement, and it's right. So you're gonna try to look for an area that kind of looks like visible waves, little tiny waves. You know, hopefully you're not going to be in a big stream where there's actually caps or anything, but little tiny places. And you're gonna so you would want to pick this side of our stream as opposed to the opposite bank, where there's not as much flow and it's a little bit more stagnant. So what you're gonna do is start point and an end point. Luckily for us, since we have 2 transects, that's our start and end point. With you guys, when you do it with your students, just measure out a distance. You're gonna go 5 meters, or if you don't have that long, shorter, but whatever it is, a consistent distance.
We went 8 meters. This is a little bit long, but we did that so that we could all have one measurement that would correlate to each of the transects. With your students, it may very well be a good idea to have one per cross section. So they are measuring the flow in their section only, and they're doing the calculations there. It's going to change the grading. I mean, it's going to challenge. Or you can do just a general flow measurement that you're going to apply to everybody's.
And it's best when you do this to have your students break up into at least a group of 4. So you'll have someone at the start point, they'll drop the ball or whatever flotation device, an orange peel, a leaf, something that will float. And you're gonna, so someone drops it, someone times it as soon as it hits the water, and then stops timing as soon as it reaches its end destination. Someone at the end destination to pick up whatever you just threw in the stream, and someone to take down the data.
And this is so fun. They'll love this. They'll want to do this all day, but you can bring some STEM into it. You can have them create their own flotation devices. They can see which one gives the most consistent results, which would be an indication that it's a good tool, because not all of these will. You'll see some will work better than others. Both
Bend
sides,
over. The stakes there. Yeah.
we put stakes on both sides of the stream so that it's very clear where the start and stop points are.
And when you do this, you don't want to step in the stream because it'll block the flow and then it'll change the flow pattern. So what doesn't look like an obstacle now, when I'm standing in it and the water's going around my boots, could then be an obstacle. So you're going to do the bend and drop.
And you can give jobs. You can have the ball watcher and the ball catcher. Please do have a ball catcher. You don't want your ball drifting off into.
Comes the SS, my lord.
I think it's gonna get stuck. All right. So what happens if it gets stuck? What do you do then? It is okay to manipulate. You can move leaves out of the way or sticks. That is completely fine to do. It does not change the flow speed.
Oh. 29.
All right, so 29 over 8 meters. How many trials should we do?
3.
So there's a line to total it and then a line to divide by your number of trials.
29.5 is our end.
So our average was 35 seconds when we did it this morning. And so, and our distance is 8 meters. So 8 meters divided by, for us, 35 seconds is 0.23 meters per second. That is your flow rate.
Because we're going to divide the meters per second to end up with that as our speed, right? That is.
So, but in addition, so that's not our final flow rate, because since we are doing it in a riffle, there's a lot more friction at the stream bed because it has to go around the rocks, it has to go through the sediment. So it's actually slower on the bottom than it is on the top of the water column. So it flows, the stream itself has 2 different flow rates depending on where you are in the water column. And since we're dropping a very buoyant object, you're getting the top flow rate and you're not taking into account the bottom. So to adjust for that, what you're going to do is multiply your flow rate, the 0.23 meters per second, times 0.85, and that's another industry standard as a conversion unit. So for us, we have 0.23 multiplied by 0.85 to get 0.19. So 0.19 is your final flow rate if you were to use our time trials that we did before you got here.
So now we have meters per second and we have meters squared, right? Those are our units. We have a measurement of the area of the water, the cross-sectional area, and we have a measurement of the speed of the water. So everybody with me so far? Meters squared and meters per second.
So with those two measurements, now you can determine the volume of water that is present in your cross-section at this time. So what you're going to do is, so you have your students answer some fun questions, and then you're going to flip the sheet, and we're going to do more math. So the flow rate that we're talking about is the final flow rate that we just said, so 0.19. So you're just transferring data over from your other sheet. And then you're going to do the same thing, transfer your data over from when you did the area, which is your meter squared. So for us, that was 0.06. So then, again, handy dandy, fill in the blank, 0.19 times 0.06. So meters per second times meter squared is meters cubed per second.
Okay.
Okay.
Volume
Which
flowing
is a volume,
past
so
this point every second.
which is 0.013. And if for whatever reason you're totally against metric and you don't like it at all, there's a conversion at the bottom to go to feet. So then you have cubic feet per second. And that's just another standard conversion of 35 point stuff times your final rate. They do, but there are some people who just object to it. So, or for whatever reason, I don't know. But yes, when you look at scientific research and you look at documents, or if you have your students do their own research, all of the calculations will be in metric. We figured out the flow rate, we figured out the area of your stream that you measured, and we figured out how much water is present in your stream. What we're just trying to figure out is pretty much just to get a baseline, so when you do come back and you do your, your checkups every year, if you want to call them that, you can see what the changes are, where the changes are, and if you want to get a little crazy with it, you could even, suspect as to what caused those changes, and have fun having your students do those kind of experiments and investigations.
So wouldn't it be more, or make it more relevant if you did a few measures a year?
Yes.
So what, seasonal or? Yeah.
Seasonal is probably preferred, but again, I understand people's schedules. It's not like you can just drop everything and say, hey kids, we're going outside today to do a couple hours of stream stuff. Or if you can, you're an awesome teacher. But most of the time, and most teachers, I think, switch students groups a couple times throughout the year, so you might not even have the same students. But I say get them out as often as you can, because that's how I got to doing what I'm doing. So.
This would also be great to send the math teachers out, though, to do this stuff. I think the math teachers would love to get out of the buildings a little bit.
And have a way to incorporate in there?
Yeah.
And you can bring this into climate change very easily because we have a lot of changing precipitation, so these banks are changing very often, and it's a really nice visual demonstration about how that's happening right in your backyard when we get these large storm events. Okay. Thank you guys so much.